In computer science, the analysis of algorithms is the determination of the amount of resources necessary to execute them. Most algorithms are designed to work with inputs of arbitrary length. Usually, the efficiency or running time of an algorithm is stated as a function relating the input length to the number of steps or storage locations. Algorithm analysis is an important part of a broader computational complexity theory, which provides theoretical estimates for the resources needed by any algorithm which solves a given computational problem. These estimates provide an insight into reasonable directions of search for efficient algorithms. In theoretical analysis of algorithms, it is common to estimate the complexity in the asymptotic sense, i.e., to estimate the complexity function for arbitrarily large input. Big O notation, big omega notation and big theta notation are used to this end. For instance, binary search is said to run in a number of steps proportional to the logarithm of the length of the list being searched, or in O, colloquially, in logarithmic time. Usually asymptotic estimates are used because different implementations of the same algorithm may differ in efficiency. However, the efficiencies of any two reasonable implementations of a given algorithm are related by a constant multiplicative factor called a hidden constant. Exact measures of efficiency can sometimes be computed, but they usually require certain assumptions concerning the particular implementation of the algorithm, called model of computation. A model of computation may be defined in terms of an abstract computer, e.g., Turing machine, and/or by postulating that certain operations are executed in unit time. For example, if the sorted list to which we apply binary search has n elements, and we can guarantee that each lookup of an element in the list can be done in unit time, then at most log 2n plus 1 time units are needed to return an answer. Cost models. Time efficiency estimates depend on what we define to be a step. For the analysis to correspond usefully to the actual execution time, the time required to perform a step must be guaranteed to be bounded above by a constant. One must be careful here. For instance, some analyses count an addition of two numbers as one step. This assumption may not be warranted in certain contexts. For example, if the numbers involved in a computation may be arbitrarily large, the time required by a single addition can no longer be assumed to be constant. Two cost models are generally used. The uniform cost model, also called uniform cost measurement, assigns a constant cost to every machine operation, regardless of the size of the numbers involved. The logarithmic cost model, also called logarithmic cost measurement, assigns a cost to every machine operation proportional to the number of bits involved. The latter is more cumbersome to use, so it's only employed when necessary, for example in the analysis of arbitrary precision arithmetic algorithms, like those used in cryptography. A key point which is often overlooked is that published lower bounds for problems are often given for a model of computation that is more restricted than the set of operations that you could use in practice, and therefore there are algorithms that are faster than what would naively be thought possible. Runtime analysis. Runtime analysis is a theoretical classification that estimates and anticipates the increase in running time of an algorithm as its input size increases. Runtime efficiency is a topic of great interest in computer science. A program can take seconds, hours or even years to finish executing, depending on which algorithm it implements. Shortcomings of empirical metrics. Since algorithms are platform independent, there are significant drawbacks to using an empirical approach to gauge the comparative performance of a given set of algorithms. Take as an example a program that looks up a specific entry in a sorted list of size n. Suppose this program were implemented on computer A state-of-the-art machine, using a linear search algorithm, and on computer B, a much slower machine, using a binary search algorithm. Benchmark testing on the two computers running their respective programs might look something like the following. Based on these metrics, It would be easy to jump to the conclusion that computer A is running an algorithm that is far superior in efficiency to that of computer B. However, if the size of the input list is increased to a sufficient number, that conclusion is dramatically demonstrated to be an error. Computer A, running the linear search program, exhibits a linear growth rate. The program's runtime is directly proportional to its input size. Doubling the input size doubles the runtime, quadrupling the input size quadruples the runtime, and so forth. On the other hand, computer B, running the binary search program, exhibits a logarithmic growth rate. Quadrupling the input size only increases the runtime by a constant amount. Even though computer A is ostensibly a faster machine, computer B will inevitably surpass computer A in runtime because it's running an algorithm with a much slower growth rate. Orders of growth. Informally, an algorithm can be said to exhibit a growth rate on the order of a mathematical function if beyond a certain input size n, the function f times a positive constant provides an upper bound or limit for the runtime of that algorithm. In other words, for a given input size n greater than some n0 and a constant c, the running time of that algorithm will never be larger than c times f. This concept is frequently expressed using big O notation. For example, since the runtime of insertion sort grows quadratically as its input size increases, insertion sort can be said to be of order O. Big O notation is a convenient way to express the worst-case scenario for a given algorithm, although it can also be used to express the average case. For example, the worst-case scenario for quicksort is O, but the average case runtime is O. Empirical orders of growth. Assuming the execution time follows power rule (TK-R), the coefficient A can be found by taking empirical measurements of runtime at some problem size points, and calculating, so that, in other words, this measures the slope of the empirical line on the log-log plot of execution time versus problem size, at some size point. If the order of growth indeed follows the power rule, the empirical value of A will stay constant at different ranges, and if not, it will change, but still could serve for comparison of any two given algorithms as to their empirical local orders of growth behavior. Applied to the above table, it is clearly seen that the first algorithm exhibits a linear order of growth indeed following the power rule. The empirical values for the second one are diminishing rapidly, suggesting it follows another rule of growth and in any case has much lower local orders of growth, empirically, than the first one. Evaluating runtime complexity. The runtime complexity for the worst-case scenario of a given algorithm can sometimes be evaluated by examining the structure of the algorithm and making some simplifying assumptions. Consider the following pseudocode. 1. Get a positive integer from input 2 if n greater than 10. 3. Print. This might take a while. 4. For I equals 1 to n. 5. For j equals 1 to I. 6. Print I asterisk j. 7. Print done. A given computer will take a discrete amount of time to execute each of the instructions involved with carrying out this algorithm. The specific amount of time to carry out a given instruction will vary depending on which instruction is being executed and which computer is executing it. But on a conventional computer, this amount will be deterministic. Say that the actions carried out in step 1 are considered to consume time t1, step 2 uses time t2, and so forth. In the algorithm above, steps 1, 2 and 7 will only be run once. For a worst-case evaluation, it should be assumed that step 3 will be run as well. Thus, the total amount of time to run steps 1 to 3 and step 7 is. The loops in steps 4, 5 and 6 are trickier to evaluate. The outer loop test in step 4 will execute times, which will consume t4 time. The inner loop, on the other hand, is governed by the value of I, which iterates from 1 to I. On the first pass through the outer loop, j iterates from 1 to 1. The inner loop makes one pass, so running the inner loop body consumes t6 time, and the inner loop test consumes 2t5 time. During the next pass through the outer loop, J iterates from 1 to 2. The inner loop makes two passes, so running the inner loop body consumes 2t6 time, and the inner loop test consumes 3t5 time. Altogether, the total time required to run the inner loop body can be expressed as an arithmetic progression, which can be factored as the total time required to run the outer loop test can be evaluated similarly, which can be factored as therefore the total running time for this algorithm is, which reduces to as a rule of thumb. One can assume that the highest order term in any given function dominates its rate of growth and thus defines its runtime order. In this example, n squared is the highest order term, so one can conclude that f equals O. Formally this can be proven as follows. Prove that let k be a constant greater than or equal to t1, t7, therefore for a more elegant approach to analyzing this algorithm would be to declare that t1, t7 are all equal to 1 unit of time, in a system of units chosen so that 1 unit is greater than or equal to the actual times for these steps. This would mean that the algorithm's running time breaks down as follows. Growth rate analysis of other resources. The methodology of runtime analysis can also be utilized for predicting other growth rates, such as consumption of memory space. As an example, consider the following pseudocode which manages and reallocates memory usage by a program based on the size of a file which that program manages. While let n equals size of file for every 100,000 kilobytes of increase in file size double the amount of memory reserved in this instance. As the file size n increases, memory will be consumed at an exponential growth rate, which is order O. This is an extremely rapid and most likely unmanageable growth rate for consumption of memory resources. Relevance. Algorithm analysis is important in practice because the accidental or unintentional use of an inefficient algorithm can significantly impact system performance. In time-sensitive applications, an algorithm taking too long to run can render its results outdated or useless. An inefficient algorithm can also end up requiring an uneconomical amount of computing power or storage in order to run, again rendering it practically useless. Constant factors. Analysis of algorithms typically focuses on the asymptotic performance, particularly at the elementary level. But in practical applications, constant factors are important, and real-world data is in practice always limited in size. The limit is typically the size of addressable memory, so on 32-bit machines 232 equals and on 64-bit machines 264 equals. Thus given a limited size, an order of growth can be replaced by a constant factor, and in this sense all practical algorithms are O for a large enough constant, or for small enough data. This interpretation is primarily useful for functions that grow extremely slowly. Iterated logarithm is less than 5 for all practical data, log is less than 6 for virtually all practical data, and binary log is less than 64 for virtually all practical data. An algorithm with non-constant complexity may nonetheless be more efficient than an algorithm with constant complexity on practical data if the overhead of the constant time algorithm results in a larger constant factor. E.g., one may have so long as n. For large data, linear or quadratic factors cannot be ignored, but for small data an asymptotically inefficient algorithm may be more efficient. This is particularly used in hybrid algorithms, like them.Most, which use an asymptotically efficient algorithm, but switch to an asymptotically inefficient algorithm for small data, as the simpler algorithm is faster on small data.